Welcome to Chapter 17, Section 5 on interference. This is going to be a bit more in-depth than what we covered in Chapter 16 on this topic. So remember that interference is the superposition of two waves. It's me taking two waves and overlapping them either temporally or spatially and seeing what happens. I add them together. If I click on this link, it brings up this website. What this website is showing is two different sources of waves. So here's the first one. I can adjust its wavelength by making it smaller or making it bigger. Notice the bright spots are supposed to be the wave crests and the dark spots are the wave troughs. Put that back down somewhere around 8. If I change source separation here, it moves the source around. And phase difference is going to adjust whether it's producing a trough at any given time or a crest at any given time. So that is wave 1. I can look at wave 2. Notice it's in a slightly different location. I can move it around as well. If I put it at 0, then it is directly on top of the other one. And then if I look at the two simultaneously, what you see here are regions where you get nice clear effect. You can still see the crests and the troughs easily. This is a region where the crest of one wave overlaps the crest of the other. The trough of that wave would overlap the trough of that wave. Therefore, we get constructive interference. In between each constructive interference region, you have this kind of mushed out gray line. This is the spot where the crest of one wave is overlapping the trough of the other. In which case, when I add crest to trough, I add down to 0, so I don't really have a wave, and that is a destructive interference range. Okay. If I change the separation, I can change how many crests, constructive interference areas and destructive interference areas I have. I can do the same thing by changing the wavelength. And I can also move them around by changing the phase, because now I'm changing where the crest of one is happening temporally compared to the crest of the other. It makes it wave. A good example of where this might be a something you would encounter in everyday life is a sound system. If you have two speakers producing the exact same sound at the same time that are on either side of your TV, so they're slightly spatially separated, for example, then in your room as you walk around, you'll hear regions where you can hear the sound really nicely, and you'll have regions where everything is kind of muffled and hard to hear. Constructive is where you can hear it well, it'd be very loud. Destructive, it would be very quiet and hard to hear. So summarizing, okay, if we get constructive interference, the peak of one wave corresponds to the peak of the other. And destructive is when the peak of one wave corresponds to the trough of the other. As we saw in Chapter 16, we can get interference either spatially or temporally. We looked at beat frequencies in Chapter 16 as an example of how temporal interference can happen. What we're building toward is understanding standing waves. That will be the subject of the 6th entry into our Chapter 17 unit. In order to get to standing waves, what we need is to understand boundary conditions. So we looked in class at the standing waves on a string, spring, and that happened when a student and I were each holding one end. So we had both ends fixed, not much happening. Then we got oscillations in the middle. Okay. In order to understand why that happens and how that happens, we need to look at what happens when waves or pulses hit boundaries. So for that, we're going to look at this website. Scroll down. So if I have a hard boundary, so something that doesn't allow the end to move, we see that as the pulse comes in, it reflects, but it reflects underneath. Okay? And if you watch very carefully, there's a point where essentially there's no pulse because the portion that is coming in is canceled by the portion that is reflected. It goes to zero. On the other hand, if I'm reflecting from a soft boundary, a boundary that is free to move, then the pulse comes in and reflects out on the same side. And again, if you watch very carefully, when it hits, there's a spot where the pulse is bigger than the incoming pulse because the reflected wave is being added to the incoming wave and therefore resulting in something bigger since they're on the same side. So summarizing that, if I'm reflecting from a fixed boundary, then I reflect to the bottom. I'm going to call that to the other side, if you will. And if I'm reflecting from a soft or a free boundary, then I reflect on the same side. Next, what we're going to look at is what happens when a wave transmits. So why is this important? If you think about, say, a trombone, pick your favorite musical instrument that isn't stringed, if you will. What we have is a wave going from inside the trombone to outside the trombone. And what happens at these different boundaries? So I believe this is the same website. It is. I just need to scroll down. So here we see a wave coming in on a light string and going onto a heavy string. The reflection here happens as if the intersection of the two strings were a fixed boundary. We can see the reflection from the on the light string is to the bottom. The other thing you might notice is that the wave moves slower on the heavier medium. On the other hand, if we look at it the other way, where we come in on the heavy string, well, that heavy string is able to whip the light string around, and therefore it is more of a reflection from a soft boundary, and the reflected wave is on the same side. You'll also notice that the transmitted wave is bigger and moving faster. So again, summarizing, if I'm going from a light medium to a heavy medium, then that is effectively a fixed or hard boundary. Whereas if I'm going from a heavy medium to a light medium, that behaves like a free boundary. In the next unit, we are going to be covering standing waves, but for the moment, that concludes this unit.